Hello, my name is Jesse Nelson,
And I'm Zach Benzerara.
and today we will be demonstrating the particle-wave duality of light using a Michelson Interferometer.
But before we get to that, we will be covering some of the history on how light has been modeled as both a particle and a wave. Christian Huygens published his Treatise on Light in 1678, where he proposed that light was a longitudinal wave. Huygens' theory had some shortcomings. For example, a continuous wave model of light cannot explain the photoelectric effect. Additionally, his theory relied on the existence of a luminiferous ether in order for his waves to propagate, but there is no evidence to suggest this ether exists. Around the same time, Newton proposed his corpuscular theory of light, which stated that light consisted of tiny particles. Since Newton was more well known in the community, his theory was more widely accepted. However, it still had some shortcomings. For example, his theory could not explain the polarization or interference of light. Newton's particle theory of light stood for around 100 years until Thomas Young's famous double-slit experiment, which demonstrated the interference of light and suggested that light was a wave. However, Huygens' theory still had its shortcomings, so scientists needed to find something new to explain Young's results. In the early 1860s, James Clerk Maxwell unified the theories of electricity, magnetism, and light. He developed a set of 4 equations that described the properties and interrelations of electric and magnetic fields, and he proposed that light itself was a transverse electromagnetic wave. For a time, it seemed as if the predictive nature of Maxwell's equations had settled the debate, and the view of light as a wave became dominant. In 1897, J.J. Thomson discovered the electron when trying to determine how fluorescent streams of electricity traveled through a cathode tube. These observations began to cast a new doubt on the wave model of light, for how could electromagnetism be a wave if electricity itself was governed by the movement of particles? In the beginning of the 20th century, scientists were performing experiments which suggested that light had particle characteristics. For example, Max Planck solved the UV catastrophe of the blackbody radiation emission spectrum by proposing that the energy of emitted light occurred in discrete packets, or integer multiples of some fundamental constant. In 1905, Albert Einstein built off of Max Planck's idea about light quantization to explain the photoelectric effect by proposing that electromagnetic radiation could be modeled as particles with wave-like properties that he called light quanta, or photons as we know them today. In 1922, Arthur Compton found that light carries momentum proportional to its wave number in his famous Compton scattering experiment, verifying one of Einstein's predictions about the nature of photons. Inspired in part by the findings of Planck, Einstein, and Compton, Louis de Broglie wrote his PhD thesis in 1924, where he proposed that all massive particles had wave-like properties and that there was a corresponding wavelength associated with any particle. Erwin Schrödinger posited that if matter had wave-like properties, as de Broglie suggested, then it should be possible to model the evolution of a particle's position over time with a wave equation. In 1926, Schrödinger published the non-relativistic version of his famous equation, which correctly predicted the spectral lines of the hydrogen atom. At this point, scientists had created a model to describe the behavior of light, which had both wave and particle characteristics. But what does this mean? Between the years of 1925 and 1927, Bohr and Heisenberg developed the Copenhagen interpretation of quantum mechanics, which states that the properties of a physical system are not definite until a measurement is made. In other words, when quantum mechanics says light is behaving as a wave, what it's saying is that it can only predict the probability that a measurement will produce a certain result, based on whatever wave equation is being used to model the system. The act of measuring a system causes this probability to reduce to one of the possible values, or collapses the wave function, because there is no more uncertainty in the outcome, which allows us to model light as a particle.
When light passes through a double slit or a beam splitter in a Michelson Interferometer, there is an uncertainty associated with which path the light will take through the system. If the intensity of the beam of light is lowered to the point that only one photon passes through the system at any given time, an interference pattern will still develop as the location of each photon striking a detector is recorded. This implies that a single photon is somehow interfering with itself, and it suggests that the photon exists in a superposition of states for each path available to it with some corresponding probability, which we can model with a wave equation. We can use this concept of superposition to explain other phenomena, like how light that is unable to pass through 2 crossed polarizers is suddenly able to once a third polarizer, oriented at some angle with respect to the other 2, is inserted in between them, or the 3 polarizer paradox. When unpolarized light passes through a polarizer, it can be described as acquiring a superposition of plus 45 and minus 45 degree states with respect to the polarization axis of the material. For example, if the polarizer is oriented at plus 45 degrees, photons that pass through the material could be described as being in a superposition of vertical and horizontal polarization states with equal probability. This superposition of states is crucial to explaining the three polarizer paradox. Vertically polarized light is in a superposition of plus 45 and minus 45 degree states with respect to the vertical axis. Since there's no horizontal component, it cannot pass through the horizontal polarizer. If we add a polarizer oriented at plus 45 degrees with respect to the vertical axis, half of the photons that made it through the first polarizer, or those with plus 45 degree orientation, are able to pass through the second one. Now the photon is in a plus 45 degree orientation, which can be thought of as a superposition of both vertically and horizontally polarized light. Since the light has picked up a horizontal component for its polarization states, the light is now able to pass through the horizontal polarizer half of the time. We can use this understanding of quantum mechanics to demonstrate the particle-wave duality of light using a Michelson interferometer and a set of polarizing materials. The diagram on the left shows a basic overview of the construction of a Michelson interferometer, with light from a source S being directed into a beam splitter M0, where it has a 50% chance of being transmitted through to mirror M1 and a 50% chance of being reflected toward mirror M2. The light is then reflected back toward the beam splitter, recombines, and an interference pattern appears on the viewing screen, B, due to the path length difference, L versus L plus D. What would you expect to observe on the viewing screen when polarizers with various orientations with respect to each other are inserted into the path of each beam? Think about what you might observe on the viewing screen if a single polarizer with arbitrary orientation is inserted into the path of one of the beams. What would you expect to see if a second polarizer with an axis orthogonal to the first was inserted into the path of the other beam? What if you added a third polarizer oriented at some angle with respect to the other two into the system? Alright, now let's start by going over the setup we're going to be using for this experiment. This is our Michelson interferometer. We have a helium neon laser that's shining into the beam splitter, and inside the beam splitter is a half-silvered mirror, which permits half the light that shines into it to pass through to this mirror, and the other half gets redirected to this mirror. And when the light reaches these mirrors, it's reflected back into the beam splitter and projected onto the viewing screen. Now, since there's a path difference between the beam splitter in this mirror and the beam splitter in this mirror, when the light recombines, you get an interference pattern on the viewing screen. Alright, now let's say that we could reduce the intensity of this laser to arbitrarily low levels, like say 1 photon per hour, so that there was only ever 1 photon in the system. Now, when the photon encounters the beam splitter, a measure of uncertainty is introduced, and if we view the photon as an indivisible particle, it could pass through the beam splitter or be reflected, but it couldn't do both at the same time. And in such a setup, since there aren't any other photons for it to interact with and interfere with, you might expect the interference pattern to disappear. But that's not actually what we see. If we were to replace this viewing screen with a detector that could register where each photon struck its surface and could output it to some computer program to display the results, and we let the setup run over time, say for a number of days for enough events to accumulate, an interference pattern would eventually develop, as you might remember from the slides that we showed you earlier. Now what that implies is that the photon isn't necessarily acting as an indivisible particle, it's taking both paths that are available to it, and it is interfering with itself. Now, we can get around the uncertainty introduced by this beam splitter by labeling each of these paths with crossed polarizers. Now, the exact orientation of these two polarizers isn't relevant. The only thing that's relevant is that they're oriented 90 degrees relative to each other, which we can easily test by seeing that they block out all light when they overlap. For the sake of simplicity, we'll say that one of these is vertically polarized and the other is horizontally polarized. So if we take this vertical polarizer and we insert it into the path of one of the mirrors, we see that not much changes with the interference pattern. It's reduced in intensity a little bit because half the light is passing through the polarizing film, and it also has a little bit of a warped shape just because the surface of this polarizing film isn't entirely smooth or polished, but the interference pattern is still there. Now, if we say we have the same setup as before, where we have a reduced intensity laser that's only allowing one photon into the system at a time, and if we say our detector can also detect the polarization of the photons that strike it, and let's say we detect vertically polarized light hitting the surface, it's possible that that light took the path through the vertically oriented polarizer, but it's also possible that it took the other path, which is essentially unpolarized, and one component of unpolarized light has vertical polarization. So since both options are still available to it, the light can continue to act as if it took both paths, and it will continue to interfere with itself. But if we label the other path with a horizontally oriented polarizer, we see that the interference pattern disappears, and it just looks like basically a red smudge there. Now what's going on here is, say we detect vertically polarized light as before, there's only one possible path that light could have taken, because vertically polarized light can't pass through a horizontal polarizer, so it had to have gone through the vertical polarizer. And in doing that, we've constrained the system in such a way that the wave function of the light collapses and it begins to act as a particle again, and it no longer interferes with itself. We can put the uncertainty back into the system by using a third polarizer that's oriented at some angle with respect to the other two. For simplicity's sake, we'll say it's oriented about 45 degrees. Now, if we insert this 45-degree polarizer in between one of the other polarizers and the beam splitter, the interference pattern reemerges. Now, at this point, the light has passed through so many polarizers that our pattern is very low in intensity, to the point that our camera isn't able to resolve the interference pattern, but we will include a digitally enhanced image that allows you to see what we're seeing here. So what's going on? If you remember, we can think of light that passes through a 45-degree oriented polarizer as having acquired a superposition of vertical and horizontal polarization. So now, if we detect a horizontally polarized photon on the viewing screen here, it's possible it took the path through the horizontal polarizer, but it's also possible it took the path through the 45-degree polarizer. And in doing that, we've reintroduced uncertainty into which path the light is taking, which means we now have to model its position with a wave equation, which is another way of saying the light is behaving as a wave again and is able to interfere with itself.
In the demo we showed you, we put the third polarizer in between the beam splitter and one of the other two polarizers in order to get the interference pattern to reappear. Where else could you place the third polarizer in order to achieve the same result? In order for the interference pattern to reappear, the light must pass through the third polarizer after it passes through either the vertical or horizontal polarizers. Placing the third polarizer in between the beam splitter and the other polarizer would also work, as would placing it between the beam splitter and the viewing screen, although in the latter case you might obscure the viewing screen with the polarizer, causing the interference pattern to be difficult to discern. The laser that was used in our demonstration is rated at 632.8 nanometers. If a student measures the appearance of 50 plus or minus 1 new bright fringes after changing the path length difference between each mirror of a Michelson interferometer by 1.6 times 10 to the negative 5 meters, what is the laser's observed wavelength? Is the laser operating to specifications? The observed wavelength can be found using the following equation, lambda equal to delta L over delta M. After plugging in the appropriate values, we find that lambda equals 640 nanometers. Since the measurement of new bright fringes has an associated uncertainty, we must propagate it to find the uncertainty associated with our observed wavelength. After plugging in the appropriate values, we find that the uncertainty is 12.8 nanometers. This gives us an observed wavelength in standard form of 640 plus or minus 12.8 nanometers. The manufacturer's listed operating wavelength for the laser falls within this range, so the student's observations do not contradict the laser's specifications.